rather briefly about the chapter that Martin Gernert and I wrote for the companion, and instead take up a little bit of the discussions of this conference and pick up some topics there. So this is a little bit on the spot, so forgive me if it gets chaotic, but hope that we can have a little bit of correspondence here between the talks, because I thought this conference is turning out to be a very interesting conversation in a way. So what our chapter was about, I'll just summarize that rather quickly, was sort of this emergence of the interpretation, what we now call the interpretation debate. And in a way, it's a big mistake to even have the word interpretation in this chapter title, because this was by none of the participants conceived yet as this very beautifully clear-cut idea of the distinction between the formalism and the interpretation that Jora presented in Maxwell's quote. So this was a theory that was just being formulated, and none of the participants had a very clear idea where things were going. And so in a way, it was mostly a debate of sort of, promising research strategies. So it was a methodological debate, and I think that is sort of the basic way where we can sort of make a distinction between mythology as a sort of, a way of going into the future, and the actual content of what was being proposed. And in the chapter, we sort of concentrate on the, basically few well-known fundamental papers and the correspondence between the authors of these papers, Schrödinger, Heisenberg, Born, and to a certain degree also Pauli and Dirac. But what I would like to sort of stress today, and I think that is sort of a nice connection to other talks in this talk, is sort of what central role the research background of the various participants took in these various positions. So what I just want to do briefly is lay out sort of, when we look at the first two formulations, quantum mechanics and of matrix mechanics and wave mechanics, that they really came from very different research backgrounds and research programs, and that the disagreement between Schrödinger and Heisenberg that then became sort of this fundamental debate had very much to do with the trajectory that they came from. Heisenberg on one hand, coming out of the Sommerfeld school, having learned basically his quantum theory just at the very end of the optimistic period of old quantum theory, veering very straight into what's now called the crisis of old quantum theory, right? The recognition of Born that the helium atom was not accessible, there was no successful treatment of the helium atom in the old quantum theory. Then the failure of the Bohr-Kramers-Slater theory to give a good, satisfying account of Compton scattering. So what Heisenberg grew up was this very shifting grounds, which led Sommerfeld then to engage in what, also ironically was then called number mysticism, right? The idea that this model building of the old quantum theory had a very limited usefulness for the understanding of atomic structure, and that basically theory should give rational reconstruction of observational results, right? I mean, there was this central idea that really informed Sommerfeld in these years, that, you know, we had these like numeric relations between intensities of emission lines and multiplets. And Heisenberg got to work very intensely on that. And Martin and I, together with Alex Blum and Jürgen Renn, wrote one paper about sort of this background of Heisenberg's work, and how that led really to the specific form of the Umdeutung paper. When you read the Umdeutung paper from a modern point of view, it's totally unclear in its structure. It's very puzzling in what he says, and I think the only way you can understand what Heisenberg is trying to do in the Umdeutung paper is as coming out of his work on multiplet intensities. But sort of with that came a whole set of attitudes about how to do atomic physics, right, that was directly coming out of this atmosphere of the Sommerfeld school. Then on the other hand, when you go to Schrödinger, he came from an absolutely different background. He had not been concerned with atomic physics in any way but peripherally, when we wrote this funny little paper how general relativity might play a role in atomic physics in the early 20s. But he came directly out of this Viennese school of statistical mechanics. And his work in the 20s, before he wrote his papers on wave mechanics, was exactly on the statistical theory of gases, and an attempt to find a way to formulate a quantum theory of the ideal gas that could explain Nernst's law. And what is very interesting about, I think, this background is that it comes exactly out of this Boltzmannian tradition of model building as a way of actually using statistical mechanics, of accessing knowledge about the microscopic world that we could never directly have. That was sort of the great achievement of statistical mechanics in the late 19th and early 20th century, that it was really the only way of assessing atomic phenomena before sort of what happened then in the post-World War period of, you know, more direct method of observation. And of course, the best example of that being Planck's work in 1900 that led to the introduction of the quantum of action. So not only was there a very clear, and I think very nicely fitting with what Jura said about the attitude of Maxwell about electrodynamics, and, you know, it's no surprise that Maxwell is also the founder of statistical mechanics, this attitude that it is absolutely necessary for a clear formulation of a theory to have a specific, unambiguous, clear model of the microworld, not because you believe that this model is in any way correct or realistic, but exactly for the sake of making specific predictions. And then you can go out and test predictions, and, you know, sometimes you're lucky and they work, and that gives you a good reason to pursue that model further. But it, of course, does not prove the model, right? The model is still absolutely speculative. But the model has to be unambiguous, right? The model has to be a very concrete, specific set of constructive elements. And so when we see Schrödinger talk about this idea of model building, it has very much sort of the flavor of what Einstein called the constructive theory, a constructive theory, namely that it needs to be this sort of system of building blocks that we can build our physical representations of phenomena of. So what Schrödinger did in the 1920s, right, in trying to find a quantum theory of the ideal gas, is just engaging in this classical Boltzmannian project of model building. And when Einstein published Bose's work and wrote his own paper on Bose-Einstein statistics, he exactly responds in this Boltzmannian sense, criticizing Einstein at first, right? And I had yesterday already a discussion with Simon about, on what grounds, right? On these grounds that he took this model very much as a classical mechanical model without any questioning sort of the mechanical basis of this model. So Simon was questioning why people even without any doubt assumed this principal distinguishability, right? What I would call nameability of particles. That particles are simply to be counted like people or macroscopic objects, while there was really in this whole community of statistical physics no questioning of this definitely metaphysical assumption. But I think that had very much to do with this sort of mechanical tradition of Boltzmannian physics, right? It didn't matter if you talk about throwing a couple of dice, or if you talk about, particles bouncing around in a container. They were supposed to follow our everyday experiences, and only then was a model sort of to be satisfied if it could be built on these like simple, intuitive elements. So Schrödinger's dissatisfaction with Einstein-Bose proposal was exactly that he immediately complained, you cannot count particles that way, right? You cannot make a combinatorics of particles according to what we now call the Bose-Einstein statistics. That's not how particles behave. And only when he then himself figured out that you could count wave modes this way, right? Because wave modes intuitively are indistinguishable. He suddenly realized that there was something attractive about Bose-Einstein mechanics, and took this as the starting point of his exploration of wave mechanics, right? Einstein had at the same time, informed, mentioned Du Bois' theory of wave mechanics, and that's how Schrödinger actually got to it. So Schrödinger came to wave mechanics as a classic Boltzmannian, and hoping that wave mechanics would be exactly this kind of a Boltzmannian theory that gave you a concrete, constructive model of microscopic events that could explain atomic physics. And at first, when he derived a hydrogen spectrum, that looked very optimistic. And so his first reaction to Heisenberg, of course, was the complaint that Heisenberg's work did not contain anything like that. And Heisenberg, of course, was not worried about this complaint. He did not think that this kind of model building was necessary at all, as long as his theory was successful in explaining the phenomena. And so as long as the two theories were really considered two different theories, right, till the spring of 26, there were still two distinct theories that had some surprising parallels, but nothing else but that. And that's how things stood. When Schrödinger and Pauli realized that there was actually this intricate connection, the translatability of wave mechanics into matrix mechanics, that's really sort of when the conflict only arose, because now it was the question of which of these formulations of obviously one theory was superior to the other. And Schrödinger's response, of course, is immediately to invoke this tangibility, or what he calls Anschaulichkeit, right, intuitiveness of his theory, as not only sort of a methodological requirement, but also sort of as the main hope for the further development of the theory. In the paper where he publishes the connection between Heisenberg and Einstein, he says a lot of the problems that we are now faced with, like developing this theory, come to us in an eminently intuitive manner. Like, for example, the problem of scattering. The problem of scattering of radiation from atoms or electrical particles is formulated to us as a geometrical picture of an incoming ray and a scattering element. There is no way we can know how to translate that into our theory without using these intuitions, which Heisenberg's theory, which was a theory of just an absolute abstract connection between matrices, does not give us. And that was a challenge that, of course, Heisenberg had to accept. Right? I mean, he could deny the need for visualizable models, but he could not deny the need to develop the theory. And so this became a topic for Heisenberg, for Pauli, and for Born. And of course, it was Born who responded. And the response of Born was, of course, not pleasant to Heisenberg, right? Because what Born used in this scattering paper was wave mechanics. He represented the incoming particle as a wave and presented the whole scattering in an intuitive form as the scattering of a wave from a atomic system. So, in a way, he exactly confirmed Schrödinger's claim that this visualizable model is necessary for the further development of the theory. On the other hand, of course, this was not the way Schrödinger had imagined that it should go, right? Because, of course, at the same time, this started the statistical interpretation of the wave function, which was absolutely not how Schrödinger imagined his waves to be understood. But that's a different story. But so you see here that the challenge for sort of giving a visualizable representation of these atomic processes becomes sort of something that Heisenberg himself acknowledges. And so he starts engaging in model building again too. But still, his idea of what is intuitive representation of quantum mechanics is substantially different from that what Schrödinger sees as intuitive model. And so when Heisenberg now over the next year works his way towards the uncertainty paper, he definitely starts some abstract way of model building he engages wave mechanics, right? I mean, the first thing you get in the uncertainty paper is the representation of a particle as a wave packet, right? So in a way, you know, taking exactly over wave mechanics. But on the other hand, not taking this as sort of any fundamental representation, but just as a visual aid in helping his argument coming from transformation theory, which in the meantime had like been formulated, about these width of wave fronts that constitute sort of the mathematical core of the uncertainty relations. So he gets this relation of delta x and delta p, and then now has to sort of try and give an explanation going beyond the fact that if we have a wave of final width, then, you know, we see that there is a relation between the dispersion in the position and the dispersion in the momentum. That would, of course, be you know, nice intuitive explanation, but that's not the kind of explanation that Heisenberg wants to get. He does not want to like give you the idea that we now have this like physical wave in space. So he needs to reinterpret that into something that follows his idea of a statistical theory, and that's where he comes up with this ingenious clue of the gamma ray microscope, right? That what this relation expresses is the unavoidable disturbance of a system by the act of observation. Right? He gives you this example of a gamma ray scattering of a particle, right? And the gamma ray has to have a minimal, has to have a short wavelength to even localize the particle. But the shorter the wavelength, of course, the higher the energy, and so the more the gamma ray disturbs the momentum of the particle. And so this is then the intuitive support for this uncertainty relation coming out of transformation theory that is supposed to give you a visualizable model of what's going on in this relation. So it's a very different idea of intuitiveness, and Heisenberg actually formulates it himself, that does not imply now having a specific model that you can constructively use, but just giving you sort of a way to physically understand an abstract mathematical relation. And what Heisenberg himself says about that in the letter to Pauli is, if you think like me that a theory is sort of understood when you have like in everyday situations good methods of a safe feeling or a sense of security in how to apply it, then you've given a satisfactory interpretation in my sense. So the Boltzmannian model is not necessary for having an intuitive understanding of quantum mechanics. And it's basically, I think, this sort of fundamental disagreement on how to deal with theories that plays out in this debate, you know, in which now also Einstein gets involved, and Born gets involved, Pauli, about what model building means in theories that drives this debate between the so-called conservatives and the Göttingen and later Copenhagen school in these early days. And I think it reflects very nicely sort of, you know, a classical debate, and that's why I think I fully agree with Jura that had happened before about the relation of theories to our pre-theoretical thinking. And I think that's good enough. Thank you.
So not only does Du Broglie in his thesis, as I was telling you yesterday, not only does he trace his mécanique ondulatoire, there's a whole chapter in his thesis about it, back to Einstein's 1917 Quantensatz paper, but even Schrödinger. So you mentioned Du Broglie's influence, his role in Schrödinger's Wellenmechanik, but Schrödinger in the Zweite Mitteilung, there's a long part at the beginning about die Hamiltonische Analogie zwischen Mechanik und Optik. And there's a footnote right at the beginning in which he does exactly the same thing that Du Broglie does. He also attributes his own Wellenmechanik to, he traces it back to Einstein's Quantensatz.
I don't remember that.
There's a footnote, the second paper.
Yeah, where he talks about the Hamiltonian.
Exactly. And he says that his own treatment closely resembles or closely follows Einstein's treatment in his. So I just wondered if you could.
I need to look at that. That totally isn't. I mean, of course. Extensively written about the Hamiltonian analogy, but that he actually refers to Einstein 1970, that is totally slipped.
Yeah, I mean, there are important differences. I suppose if one looks for them, one can see analogies. I mean, in both cases, they're waves or they're surfaces of equal something or other propagating in configuration space. So maybe that's what he has in mind.
Seems hard to square. I gotta look back at that. Yeah, that is possible.
Yes, you pointed out that much of the different views concerning quantum mechanics between Schrödinger on the one hand and Heisenberg on the other can be traced back to their different backgrounds, their different research tradition for where they came. Heisenberg coming from some of the Bohr school with a strong emphasis on atomic theory and spectroscopy, and Schrödinger from a very different tradition. He had not worked in atomic theory and atomic models, but I want to point out that there was at least one common ground between these two different traditions, namely, and that Schrödinger was not a foreigner to atomic models. So I want to point out that in 1922, I believe it was, he suggested this modification Bohr's atomic model with so-called penetrating orbits, Tauchbahnen in German, in which the elliptical orbits dips into the inner structure of the atom. And that theory, I mean, was very much in the Bohr-Sommerfeld tradition.
Definitely.
He covered both grounds.
Stylizing the backgrounds a little bit, because Schrödinger did really a lot of different things, right? I mean, he was all over the place, but he certainly was not like imbued like somebody like Heisenberg in this active work, and especially not in the years leading up to 26. As I said, right? I mean, the last 2 years were all, very centrally about gas theory. So yeah, it's definitely true that it was not just like that. And of course, also Heisenberg did other things than build work for Sommerfeld. Right? I mean, one thing he later talks about how impressed he was by the theory of relativity and how much he admired Einstein. So that's a whole different story. But yeah, that was a simplification.
One last question.
This is a really question. The first phrase of Heisenberg first paper for the mechanics start with the following expression. In this paper, I use only observable values. Only observable. So he was influenced by Ernst Mach
wouldn't say directly by Ernst Mach. I think the direct source of that is exactly the Sommerfeld program to sort of reduce the model building at atomic physics by by concentrating on relations between, in Sommerfeld's case, these multiplet spectra intensities. So this general feeling that there had been too much excessive model building in the old quantum theory, and that had not really led to the successes from it. Of course, all that went back into a longer tradition, and didn't come from nowhere. Is obviously understood, but that was sort of the close background of that. Of course, he's been also accused in a lot of the literature of this, I'm talking about only observable quantities being purely window dressing and not really any serious commitment. I think it's somewhere in between, right? I mean, it has this very concrete meaning of because then he very quickly abandons this talk about only observable quantities, right? I mean, it's a rather temporary phenomenon, but I think that is sort of really where this sense of using observable quantities comes from.
Well, this concludes our session for the morning, and thank you very much.
And the lecture is for the floor. I think for participants, you can follow your